Hey everybody, welcome to chapter 11 and our second lecture video. So this chapter is on alkanes. So alkanes aren't something that we mentioned in the functional group. Well, I mentioned it, but the book doesn't mention it because it isn't a group of atoms or atom attached to any particular molecule. An alkane is that parent molecule that you would stick a functional group on. So this is why we're starting here. It's the simplest of the organic compounds. Now, just to jump right in, we are talking about hydrocarbons. Hydrocarbons are compounds that are composed only of carbon and hydrogen. And there are a few different classes, and you can see that we are going to go through them in different chapters. We're going to start here in chapter 11 with alkanes, and then we'll go on to alkenes, alkynes, and arenes, or aromatics, as they're more modernly referred to. Modernly, I don't think that's a word. So what we're talking about here are hydrogen and carbons, and these are going to be differentiated by the number of bonds that they have between carbons. So you can see here for our alkanes, we have simply single bonds in between each carbon. Alkenes and alkynes have double and triple bonds, so we'll look at those in chapter 12. And our aromatic compounds are going to be ring structures that have conjugated systems, and we'll talk about what that is when we get there. So to start off, alkanes are going to be the simplest hydrocarbons with single bond only. Now, as we move on, we can start to worry about naming. And so let's just take a look at first the simplest hydrocarbon of them all, a one carbon molecule. And then we'll take a look at the next simplest, or I guess the next more complex hydrocarbon, which has two carbons. And you can see that with our first simplest alkane, with only one carbon, there's no single bonds to other carbons you have to worry about. We put all the hydrogens on here, and I'm gonna introduce this now. We call it saturated when carbon is holding as many hydrogens as it can. Carbon loaded with hydrogen. And just to show you how we can start to not be saturated, let's take a look at the two carbon alkane. So again, we see the single bond in between the two carbons. Now, if this wasn't saturated, it wouldn't be able to hold the maximum number of hydrogens, which is in this case 6. Each carbon can hold 3 hydrogens because its fourth spot is used up bonding to the other carbon. If I was to draw a carbon that had 2 double bonds to each carbon, this only allows now for each carbon to hold 2 hydrogens. And of course this would be an alkene and not an alkane because it has a double bond, but then you can see here that it would be called unsaturated. And this would refer to that it doesn't have as many hydrogens as it could have. If this wasn't a double bond, it could hold 2 more hydrogens. Okay, so these are our alkanes of the simplest variety. Now, as we start to get into more complex alkanes by adding additional carbons, we're going to get into a few different problems. We're going to get into some isomers. So before that, let's just talk about the general structure and representation of alkanes. So we use something called line angle formula. And these line angle formulas represent the carbon-carbon bonds. Now, shown here are the ball and stick models, the condensed structural formulas, and then the line angle formulas. Now, I really like line angle because you can draw, for example, pentane has 5 carbons in it. Writing this out takes a certain amount of time, but saying, okay, carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon is really easy. And so to point out, every corner and end of these line angle structures is a carbon. It is, what's the word? It's taken for granted, that's not what I'm trying to find, but this works. We can take it for granted that there are saturated, or that every carbon is saturated. And we know that because we don't see any double bonds. And I hope the previous slide here can help illustrate why a double bond automatically means that we are unsaturated and have less hydrogens. So no double bonds, we can assume these are saturated. That means the ends will have 3 hydrogens, and every middle carbon will have 2 hydrogens. And that makes sense because each carbon is tied up with 2 of its 4 bonds just getting to other carbons. So that only leaves 2 for the hydrogens. And again, you can see that if you look at the ball and stick models. Okay, so this is the representation of the 3, 4, and 5 carbon alkanes. You can see here that we're going to be able to name all the way up through 10 carbon chains. Now, at some point in this class, we are going to be naming compounds and drawing compounds, and so let's go over a little bit of the systematic way that we name these. Actually, we're going to get to that. Let's talk about constitutional isomers first. I think that's where my brain was going a little earlier. When we start getting to carbons, let's say 4 and 5 and above, we can start putting together these carbons into different configurations. For example, if I have butane, which has C4H10, I could put that as C4, all 4 of my carbons in a row. Now, I'm not going to put all the hydrogens in. We know hydrogens would fit everywhere on here. But I could also arrange this as 3 carbons in a row with a branch off of the middle carbon. Now, this will still give me 10 hydrogens. And so what we would call these 2 compounds are constitutional isomers. So a constitutional isomer is a compound that has the same molecular formula, but a different structural formula. That just means that the formulas are identical, but the way that they're connected is different. And as we start to get more and more carbons, we're going to see that there's more and more different ways that we can hook them together. Now, there are some really they're alkenes and alkynes that don't have constitutional isomers, and this is going to be because they're going to be unsaturated. But as long as we're talking about saturated, there's going to be multiple ways that we can connect compounds together. I think here is that example that I just showed you. Butane, 4 carbons in a row, and then 3 carbons in a row with that branch. Now, now these are different compounds. They have different physical and chemical properties, different boiling points, for example. Their boiling point differs by about 11 degrees. And so we saw a couple constitutional isomers actually in the last chapter. When we were doing those examples, we were saying, draw 2 alcohols that have this formula. Those are constitutional isomers. They're the same formula, but represented or drawn differently. And this is going to come back again when we start to name compounds. What I mean is, let's say that I have a 10 carbon chain. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a 10 carbon straight chain. Now let's say that somewhere on this carbon chain, I have we're going to call it a substituent. Now, functional groups can be substituents, but we would typically call them, the alcohol group or the amine group, right? Because they're functional groups. Alkanes aren't themselves functional groups, and so when we have branches off of, let's say, a decane like this, that's a 4-carbon branch, we would just call it a substituent. So there's two ways that I could put a 4-carbon branch on here. I could, 1, 2, 3, 4. I can stick butane as a 4-carbon branch, or I can actually stick, so 1, 2, 3, 4. I can stick 2-methylpropane on to this long 10-carbon decane as a branch. And so because both of these have the same formula, and because they're constitutional isomers, they present a situation where when we're naming what this now decane is called with these groups on them, we would give it different names depending on whether group A was on this decane or group B was on this decane. Even though it's the same formula, same number of carbons, even if they were on the same position, if this guy was actually attached right here instead, they would still get different names because 2-methylpropane is different than butane. They are connected differently. So that makes part of our job a little harder in this class, because we have to now recognize when we have constitutional isomers and that they might be named different. So let's try one. So do the structural formulas in each of these sets represent the same compound or constitutional isomers? Go ahead and pause the video, because I'm not going to work through it. Pause the video, look at it, give it a shot, and then I will give you the answer here in a couple of seconds. Okay, so for A, these are the same. They're the same compound, and we know this because they're all connected in the same way. Carbon 1 is connected to 2, 3, 4, 5, and 6 in a straight chain. 1, 2, 3, 4, 5, 6 in a straight chain. There's a kink in this chain, the way that it's drawn, but that doesn't change the fact that every carbon is connected in a big long line. What about B? These are constitutional isomers. So we can see it best when we sort of redraw this. 1, 2, 3, 4, 5. So we have a chain of 5 carbons, and we can see that there's a branch on the number 2 and on the number 4. And if we look at this other one, we can see that there's a branch on the number 2. I drew this backwards so that I just flipped this one around. 1, 2. And we can see that there's a branch on the number 3. I just flipped it around so that the naming or the numbering would look the same here, so we can kind of see the difference. But these would be different. And again, you just look at where they're connected. You can kind of see it here. This carbon has 2 carbons, actually has 3 carbons on it. 1 here, and 1 here. That's this carbon right here. 1, 2, 3. Where we don't see that, or we see 2 of those in this compound. We don't see 2 of those. No, I guess we do still see 2 of them. They're just right next to each other here, and they're separated by 1 here. This is going to take a little bit of practice for you guys. I'm not going to lie, but that's why we're doing it. Draw the structural formula for 5 constitutional isomers of a molecule with the molecular formula C6H14. Okay, so go ahead and pause it, pull out a piece of paper, give it a shot. I'm going to draw them in 3, 2, 1. So we've got 6 carbons here. First one is easy. Just put them all in a row. 3, 4, 5, 6. What I like to do is start to shorten my chain. I'll show you what I mean. So 2, 3, 4, 5. And now I've got one more I can stick on. And it doesn't make sense to put it on either end, because that would just give us back what we had before. So my only options are to stick it on one of these other carbons. So I'm going to put it here. Now, I see that there's another choice. I could have put it here. I can't put it here because that's the exact same thing as putting it here, right? This is the second carbon from the end, and this is the second carbon from the end. It would literally just be like this, right? These are not constitutional isomers. It's just this guy flipped around. So you gotta be able to watch that. So we have 6, 5 with 1 there and 1 there. Sorry about that. So on one of the second carbons and then on the middle carbon. And then again, I can't do another one with 5 in a row or else I get into repeats. So now I'm going to go to 4. 1, 2, 3, 4. And the same thing, I can put 2 carbons on here, but it wouldn't make sense to stick them on the ends, or that just grows my chain. I can put them on either this carbon or this carbon, and I can do it in 2 ways. I can put the 2 carbons that I have left on the same carbon, or I can spread them out. So what I mean is, I can put 1 carbon, 2 carbon on the same carbon, or I can just put 1 on that carbon and 1 on the other carbon. So in all cases here, I only have 6 carbons. Now, can I go even less? 1, 2, 3. Now, no matter where I put my other 3 carbons, I'm going to get a previously drawn structure. For example, I can put 3, 4, 5, and then I have to put it somewhere else. Let's just get crazy. Put it here, 6. So it looks like I have a 1, 2, 3, 4 in a row, and then 2 carbons coming off of this, the second one. Well, that's this guy. So I already drew it. So there's basically no more that we can draw. This one is the first repeat because there's no 3 carbon chains that we can make that'll still support 3 extra carbons and not have been drawn already. So 6 carbon, 5 carbon, 5 carbon chain, 4 carbon chain, 4 carbon chain. Now they still all have 6 carbons. So take the time to make sure that you can see that. Now if you're not drawing them this way, that's okay. You could be drawing them like CH3, CH, CH3, CH2, CH2, right? CH3. You can do that too. I tend to find line angle to be much more convenient. And obviously you write out less, but in the beginning I really do encourage you guys to maybe do it this way so that you can appreciate drawing it like this, because you do have to do it like this a little bit so that you know how many hydrogens are there. Like it's not intuitive to remember to stick a lone hydrogen here because there's one here. You know what I mean? You don't see it, you forget about it, but it does help in the beginning to write them out that way. Okay, let's move on. Let's move on to naming. So the name of an alkane with a branched chain, well, we should probably learn just the regular unbranched chains first, but we'll give you the whole rule. So the name of an alkane with a branched chain of carbon atoms consists of 2 things. It comes with a parent chain, and then it comes with the substituent name. Now the parent chain is going to be the longest straight chain of carbons, of hydrocarbons. And then the substituent is going to be named with a slightly different ending. So let me kind of give you a few examples. So let's say that I have 2 carbons in it. Well, actually, we need to see how to name parent chains. So let's introduce this. So these are the prefixes that we use. And you can see here that there's some missing numbers. So 6, 7, 8, 9, and 10. So if I have 2, 3, 4, 5, 6, 7 carbons, then the prefix would be hept. Now because this is an alkane, we're going to name it ANE, so heptane. If this was an alkene that still had 7 carbons, the only difference is that for alkenes we name them ENE. So this would be heptene. But it's not. This is heptane. So there's, oops. So that's one example. Let's try another one. 1, 2, 3. So we look up 3. It says it's prop. So this is prop. And again, it's an alkane. So we'll name it ANE. Just to give you guys an idea of how this works, if I wanted to stick an alcohol group onto this 3-carbon molecule, it would still be prop. Actually, it would still be propane, and then alcohols get OL endings. So this would be propanol. So propane, propanol, if this was an aldehyde, aldehydes get named with an AL. This would still only have 3 carbons in it, so it would be propanal. So we're going to use the number of straight chain carbons in our naming. Now, to go back over here, let's kind of see what's happening. So we've got 8 carbons in a row. You look for the longest chain. And so let me do another one. 2, 3, 4, 5, 6, 7, 8. And then let's take 1, 2, 3, 4. So let's name this guy. First, we have to find the longest chain. So I already numbered them. 1, 2, 3, 4, 5, 6, 7, 8. But we need to check anyways. So how about 1, 2, 3, 4, 5, 6, 7, 8, 9. If I number this way, I get a 9. What about 1, 2, 3, 4, 5, 6, 7, 8? Okay, so it looks like by numbering the other way, I actually get a longer chain. So this would be then nonane. Nonane because non-known is these are Latin, I believe. So just prefixes. Nonane. And then we would say, okay, on the 1, 2, 3, 4, 5, there's a branch. Let's just make sure that that's on the 5. Let's go this way. 1, 2, 3, 4, 5. Yeah, it's 5 no matter which way we number. And what's important about that is we always want to give the substituent the lowest number. Because you could have numbered this way. 1, 2, 3, 4, 5, 6, 7, 8. And then we would call this 5-methyl octane. But if we number this way, we would call it 4-methyl octane. So we don't want confusion based on which side you started numbering. So we'll always give it the lowest number. So in this example down here, on the number 5, we have a 1, 2, 3 carbon substituent. So we know that it's 5-something nonane. Now it's a 3-carbon substituent. 3-carbon alkanes are called propane. But we don't say 5-propane nonane. You'll notice that there's a YL in here. So, right, and the simplest alkane that we learned was methane. Do you remember that? Methane from 10 minutes ago? Methane, you can see for 1 carbon, meth is how we would name that. So methane, you can see here in the naming of 4-methyl octane that it's been turned into methyl. Instead of methane, it's methyl. That's what we do to substituent names. We put a YL on them. So propane, this propane group is going to become a propyl, and we'll say 5-propyl nonane when it comes to the molecule I've drawn. 4-methyl octane when it comes to this parent chain or this main example. So you guys are going to want to practice. I don't know what just happened to my... Okay. Pen stopped working for whatever reason. So you're going to want to practice drawing out at least some straight chain alkanes, and then maybe starting with some drawings, try to go back and name them. to make it interesting, you should put substituents on them. So let's look at some common alkyl substituents. Now, when it comes to the first two, methyl and ethyl, there's only one way to attach a 1-carbon or a 2-carbon group to a longer molecule. But when it comes to these others, the 3-carbon molecules, the 4-carbon molecules, and beyond, you can see that, remember, constitutional isomers start to happen. Now, there isn't a constitutional isomer between propyl and isopropyl. These are just 3 carbons in a row. But because we can attach it to the parent chain at either the end of our 3 carbons in a row or the middle of our 3 carbons in a row, we can get 2 different propyl groups. They tend to make, whenever they're attached in the middle like that, so another way of sort of showing this is if I've got a carbon compound, here's my propyl. Right? Here's my propyl. Those 3 carbons attached at the middle. Sorry, I should say isopropyl. Here's my isopropyl. It kind of looks like a Y. And I know that iso is not YSO, but isopropyl and isobutyl tend to have Y-type shapes. Let me show you. So isobutyl is 1 carbon, 2 carbon, oh my bad, I drew it wrong. It's actually got a carbon before the other carbon. But it still has this sort of Y shape in it. These are the 4 carbons, 1, 2, 3, 4. These get the iso name. So I'm just kind of telling you that because that's how I remembered it. Whenever they're the straight chain versions, we just say propyl or butyl. Isopropyl is the only other version for propyl, but butyl actually has a few other versions. And so the way that your book, I think, does it is they say, how do you convert a butyl group into an isobutyl group? Or how do you convert a butyl into a sec-butyl, or into a tert-butyl? And so it makes more sense for sec-butyl probably, because if you look, at least for sec-butyl, these carbons are all in a row. And the difference between butyl and sec-butyl is that instead of attaching to the end of the carbons, it's actually attached to the second carbon, hence sec-butyl. These are still in a row though. You see that with tert-butyl and with isobutyl that they aren't in a row. These have 3 carbons in a row with a branched carbon, 3 carbons in a row with a branched carbon. Now the difference here is that you can either attach at the end of your 3 carbons in a row, or you can attach at the middle of your 3 carbons in a row. This is probably going to be a challenging part for you guys, but again, well, let's do an example. So let me give you this. Actually, we'll do it like this. So you may have to, let's say, name this compound. So the first thing you would do is try to find the longest parent chain. I didn't make this one a tricky one, so we should be able just to look at the long chain here. So 1, 2, 3, 4, 5, 6, 7, 8, and I probably should have numbered it the other way. So we'll number it the other way. 1, 2, 3, 4, because that gives us a lower number for our substituent. 5, 6, 7, 8. So this is octane, and we know it's 4 something octane, because on the 4, we've got a group. Now, how many carbons are in our group? 1, 2, 3, 4. So this is some sort of butyl. And again, you'll have to learn these meth, eth, prop, but, pent, hex, hept, oct, non, dec. We're not going to name more than 10 carbons long. So butyl is 4. And then we have to decide, is this regular 4-butyl octane, or is this sec-butyl octane, isobutyl octane, tert-butyl octane? And so you can probably see, or you already saw, that it's attached at the second carbon in our straight chain. So that makes this guy sec-butyl. And so that's what you would write, 4-sec-butyl octane. If this was regular butyl octane or tert-butyl octane, then instead of being in a row like that, we might see something more like, right, where the 4 carbons are arranged sort of in a T, like tert-butyl. So this is just with regular alkyl substituents. We haven't gotten into the fact that we can add double bonds or triple bonds or start adding functional groups yet. So this is one of those moments where you have to kind of think, hey, is this something I can do? Is this too hard? Am I going to be able to learn this? Because it's only going to get more involved. All right. Is this a practice? What am I showing here? So as far as naming goes, just to kind of recap, the name for the alkane with an unbranched chain of carbon atoms just consists of a prefix showing the number of carbon atoms and then the ending ane. So 1, 2, 3, so prop-ane. For branched chain alkanes, the longest chain is the parent chain, and it's the root name. And then each substituent is given with a number. And so this substituent here on number 2 is a single carbon group of methyl, so 2-methylpropane. And if there is one substituent, as I mentioned, we do want to give it the lowest number. So here's an example of that. Here, if we numbered 1, 2, 3, 4, 5, we would still call this pentane, but we might call it 4-methylpentane. And so we want to give it the lowest number. If there is a substituent that occurs more than once, this happens. So if the same substituent occurs more than once, then you number the parent chain from the end that gives the lowest number to the substituent encountered first. So if we numbered this way, 1, 2, 3, 4, 5, 6, the fact that our first one is a 3, whereas this way our first one is a 2, means that we're going to go with the 2. You indicate the number of times the substituent occurs by giving it a prefix, like di, tri, tetra, penta, hexa, and so on. So in this case, we have 2 methyl groups. So that would be a dimethyl. Everything else is still the same. I apologize. We have to actually mention where those 2 numbers are, and we separate them with a comma. So in this case, it's going to be 2,4-dimethylhexane. If they were on the same carbon, this is still dimethyl, this is still hexane, but this would be 2,2-dimethylhexane. So multiple substituents get separated you separate their numbers by a comma, and then you say di, tri, tetra, and so on. If your substituents, though, happen to be different, then we list them in alphabetical order. So in this case, we've got 2 groups. On the number 5, we have a methyl, and on number 3, we have an ethyl. So E comes before M, even though, what I was going to say is sometimes they have lower numbers. So for example, if we had on the 3 a methyl and on the 5 a ethyl, we would still, actually this is the same. 1, 2, 3, 4, 5, 6, 7. Here you can't, no matter what side we number from, we're going to get 3, 5. So the problem with numbering, or the problem with this that some students see is sometimes you can name something two different ways. The goal at the end of naming is to be able to draw back the molecule. That's the only purpose. We want someone to be able to recreate the structure that we have. So we're naming it systematically so they can do that. If I called this 5-ethyl 3-methylheptane, I would still get the exact same structure. And so in that sense, this thing could be named 5-ethyl 3-methylheptane, but it could also be 3-ethyl 5-methylheptane. Now, depending on where you put the groups. Now, in specifically this molecule, this one is 3-ethyl 5-methyl, and it's 3-ethyl because the E comes before M. In this molecule specifically, we would say this is 5-ethyl 3-methyl. Notice that we're not saying 3-methyl 5-ethyl, or 3-methyl 5-ethyl. It's not the same name over here. This one's different because the E is on a different numbered carbon, but also comes first. E comes before M. These are the same structure. We can name them different ways depending on which side we start numbering. We're not going over the rule that says when you encounter the number 3 for both of these groups, which one actually gets it. If we were doing that, we would probably give it to the bigger group. But we're not going to do that. We're not going to worry about those kind of things here. We're happy just getting the naming. And again, if you numbered this one the opposite direction, it would still work and you would still be able to recreate it. The only thing that would be different is that these numbers actually would be switched. The ethyl would still go before the methyl, but the ethyl may end up with a 5 instead of a 3. Okay. If there is some, let's see, I'm trying to see what my point is. We want to alphabetize the name of the substituents first, and then insert prefixes. So what I'm getting at here is that we've got some dimethyls here. We don't want dimethyl to actually influence the fact that D goes before E. So what I'm saying is ethyl goes before methyl. Dimethyl alphabetically comes before ethyl, but we don't take the di, tri, tetra into account. Okay, this compound here has 6 carbon straight chain, so it's hexane. It has 2 methyl groups and an ethyl group. So the ethyl group goes first, the methyls will go second because of alphabetical order. We're going to say 4-ethyl because it's on the 4, and then we're going to say 2,2-dimethyl because there are 2 methyls on. So 2,2 because they're both on the number 2, and di because there's 2. Let's see. Does your book have a good problem I can give you right now? Let's try this one. So this is from your book. All right. So pause the video, give that one a shot, and then I'll give you the answer in 3, 2, 1. All right. So we want to number this by longest parent chain first. So I'm going to just do some quick numbering. So 1, 2, 3, 4, 5, 6, 7. If I go that way. 1, 2, 3, 4, 5, 6, 7, 8. If I go that way. 1, 2, 3, 4, 5, 6, 7. Okay, so I think the parent chain is there. So 1, 2, 3, 4, 5, 6, 7, 8. As opposed to the other way, which would put this carbon down here at number 5. So then on the 4, we've got two set of groups. We've got a 3-carbon group, which is arranged in an isopropyl configuration as a substituent. And then we've got a 1, 2, 3-carbon group here, which is just a straight propyl group. They're both on the number 4. So what we would say here, isopropyl comes before propyl alphabetically. So this is 4 isopropyl, 4 propyl, 8 carbons, octane. 4 isopropyl, 4 propyl, octane. So just as an example from your book. All right. Now there are some common names that are from an older system. The number of carbons actually determines the name. The first 3 alkanes are methane, ethane, and propane. And all alkanes with the molecular formula C4H10 are named butanes. All of those with the molecular formula C5H12 are called pentanes, and etc. For alkanes beyond propane, iso just shows that one end of an otherwise unbranched chain sort of terminates in CH3CH, so like this. So anytime you have iso, it just means that you've got this happening somewhere. So in the case of isopropyl, this is what we have just sticking onto our group. In the case of isobutyl, there's another CH2 in here, CH2. And then I'm sure in the case of isopentyl and isohexyl and all that, that just means that this part grows longer and longer as it connects to the bigger molecule. So this would be, if this was the group right here, this would be 1, 2, 3, 4, 5, 6. This would be isohexyl. So just to kind of show you how that works. Okay, so that's a common name sort of explanation there. So where do alkanes come from? Most of it comes from the earth, right? So we have petroleum that we can sort of get out of the ground. These are old, we say that these are fossil fuels. They come from decaying organic matter, and then we can actually refine that. So let's just talk about some sources of alkanes. There is natural gas. This is about 90 to 95% methane. So the simplest hydrocarbon. And it's got actually about 5 to 10%, depends on the mixture of ethane as well. And this is so natural gas is a mixture, there's a few other relatively low boiling alkanes, but chiefly among these would be maybe propane, butane, and 2-methylpropane, which is a constitutional isomer of butane. So just all the smallest sort of hydrocarbons. These tend to exist as gases anyways. And then we have petroleum. Now this is a thick, viscous liquid mixed of thousands of compounds, most of them hydrocarbons, formed, like I mentioned, from the decomposition of animals, marine plants, and so forth. And so petroleum actually gets refined. And so we can take this petroleum, and what we do is we basically separate it by heating it up. And so as we start to boil it and get it hot, the gases of all the low, carbon 1 through carbon 4 type hydrocarbons, these sort of come out, and we use these as fuels, we use these as reactants, as it says for plastics. The next bit that comes out is the gasoline, so about C5 through C12. The common component of gasoline is octane, so C8. This is used, of course, for other types of motor fuels and solvents. After that, C12 to C16 type hydrocarbons, we would call that kerosene. These have higher boiling points. Lamp oil, diesel fuel. Then we get the C15 to C18 hydrocarbons. Again, catalytic cracking, heating oil, diesel fuel. Lubricating oils come out after that, C16 to about C20. And then anything that's left over, these are large hydrocarbons, and we would use this as oil or asphalt or something like that. So that's basically where they come from. Now, we have cyclic alkanes as well, we call these cycloalkanes. There's cyclic hydrocarbons. So these, of course, are going to be unsaturated because the carbons have to reconnect to themselves, on the two ends. So we're going to lose a couple hydrogens there. A cycloalkane is a cyclic hydrocarbon in which all of the ring is saturated, but they have only one single carbon bond. And again, the difference in the formulas, we would still say it's saturated because they're holding as much as they can, but compared to, let's just say this is 6 carbons. So normally for 6 carbons, you have times 2 plus 2, the number of hydrogens. So for a straight chain of hexane, we should have 14 hydrogens. This molecule here of this cyclohexane only has 12 hydrogens. So it's less saturated in respect to an open chain structure, but it is saturated in the sense that we haven't put a double bond in here. Okay. So cycloalkanes with ring sizes from about 3 to over 30 carbons are found in nature. We tend not to find rings of 3 or 4 very much because there's a lot of strain here. There's a lot of repulsion from these atoms. They don't like being that close together. And of course, you need at least 3 to make a ring. You can't do it with 2 carbons. 5-membered rings, cyclopentanes, and 6-membered rings, cyclohexane, are especially abundant in nature. And as far as the naming of these go, to name a cycloalkane, the prefix of the name of the corresponding open-chained alkane with cyclo. So for example, this one here has 5 carbons. So it's pentane because of 5, but it has cyclopentane because it's a ring. This one here is 6 carbons, so it's cyclohexane. Now, if there's only one substituent on the ring, there's no need to give a location number because it doesn't really matter, right? We wouldn't say 1, 2, this is 3 isopropyl cyclopentane. It's sort of arbitrary to count this as the number 1 for no reason. We would just as easily just say, well, this is 1 isopropyl cyclopentane, right? Why not just give that carbon the number 1 so that the group is on the number 1 carbon? In that sense, we don't even need to say number 1. So that's what they're saying, what your book is saying. So if there's only one substituent, you don't need to say its location, you just say what the group is. In this case, it's isopropyl cyclopentane. Let me give you another one. This is a bromine. We're going to do the same thing. We're going to give it a YL ending. So this would be a, actually we don't give it a YL ending, we give it an O ending. So this would be bromo. Bromo, cyclo, with 4 carbons, it's bute, so cyclobutane. If it was a chlorine, you'd say chloro, but you wouldn't have to say 1 chloro, 1 bromo, or anything like that. If there are 2 substituents, then you do number the rings beginning with the substituent of lower alphabetical order. So because in this case tert-butyl, B, is before methyl, M, we would give that one the number 1 and then number everything relative to that. So if this group was here, we wouldn't number this way, we'd number this way in order to give it a lower number, right? Because this could be 3, but it could also be 5. So, so just pointing that out. So when we're numbering this guy, we would say 1, 2, 3, and then that would be the 4. We would still give both of these their substituent names, methyl and tert-butyl, but we would say 1 tert-butyl, 4 methyl, cyclohexane. Yeah, I like ring structures. They're not that difficult. Just remember to say the word cyclo. We want to put the word cyclo in there, and then yeah, the same other rules apply. Alphabetical order for substituents, numbering from, in this case we're numbering from the lowest alphabetical one. So in order of alphabet, that's how the order of number will go, which is different from straight chain. Let's talk a little bit about the conformation of alkanes. Alkanes can have a few different arrangements, 3D arrangements. And this is because there's free rotation around single bonds. Okay, so you can see here in this butane molecule that there's a least crowded conformation where all the molecules are sort of as far away from each other as possible. Now, there is a situation where we could rotate this bond in a way that this group is now up here. And so you can see that here. Now they're right next to each other. Now, this is a crowded conformation, and nature, again, there's electron clouds in all of these atoms. They're going to push away from each other. And so what we're going to talk about is, when we get to the rings, we're going to see that rings will actually take on a specific sort of conformation. But anyways, you can see here that there is free rotation around these bonds. That just means that these groups can and will move away from each other if they get too crowded. Okay? We're going to learn later on in the next chapter that when we introduce a double bond, we actually stop the rotation around these bonds. A double bond doesn't rotate. So if this had a double bond in it right here, instead of a single bond, we actually would not see this guy ever coming up here. It would be locked in place. So that's a cool thing about single bonds that double bonds don't have. Now, when we expand this to talk about rings, I forgot to mention cyclohexane or cyclopentane. The most stable conformation of a cyclopentane ring is actually something we call the envelope conformation, and you can kind of see it here. It looks like, the four guys are here, and then there's like the little envelope tab, right? Four atoms, and then the fifth up top, like an envelope, right? Folds over. So that's the most stable conformation for this guy, and it makes sense because all of the groups are sort of pointing away from each other, right? They're all pointed away. Nothing is crowding. When we get to six-membered rings, we start to see same kind of thing. The most stable conformation of a cyclohexane ring, which is six-membered, is called the chair conformation. So you can kind of see, let's see, am I showing you chair? Yeah, this is the chair conformation. I'm going to show you the other conformation here in a second. So this is chair conformation in the skeletal mode and the ball and stick, and then viewing from above. From above, you can see it makes sense. A lot of these guys are all spread out from each other. From the side view, you can also see that the atoms are up, or they're down, or they're sticking out at the sides. So nobody's overlapping, nobody's getting too close. We actually call these two positions axial and equatorial. So you can see if we were to look at the ring and all of the hydrogens that are sticking out sideways, we call those the equatorial hydrogens. And all of the hydrogens that are up and down, we call those axial. And there's 6 in both cases. Now, the two different conformations of cyclohexane actually change how many equatorial and axial hydrogens there are. So I'm trying to show you, actually this is a substituted group. With a substituted group, you can kind of see it a little better too. So I'm going to just show you this first. So here we have a substituted cyclohexane ring, and you could probably figure out which one of these is going to be the more stable conformation, because these things flip back and forth between conformations, but they spend more time in the one that's more stable. So what do you think by looking at this? You can see here that in one view, when methyl is equatorial, it doesn't interfere at all with these axial hydrogens. Yet when it's axial, it actually has some interactions with them, right? You can see it better in the space filling model. So the more stable way to stick a substituent onto a cyclohexane is to stick it equatorially. If we go back here, let's see, to this slide, I think I have something here to show you. You can see here versus, we're going to talk about cis versus trans. So cis means same side, trans means opposite sides, and this will come back to when we talk about double bonds. But here with the ring, it means are the two groups on the same side of the ring or on opposite sides? And you can see here with a di-substituted ring that there's going to be a conformation that's going to be more stable than another. Having both of these dimethyls cis means that they're both on the same side and they're bumping into each other. Having them on opposite sides of the ring, now they're still connected to the same two carbons, right, that are right next to each other. But having them oriented in a way that they're pointing away from each other is much more stable. This isn't something that you would have to draw or predict, but it is something that you should know about the nature of ring structures. Ring structures that have one group are going to try to stick them equatorially. Ring structures that have two groups, ideally they would be in the trans configuration. Now that doesn't always happen. They get stuck sometimes in when the ring closes, these groups might be on the same side. But that is going to make that a more stable, a more unstable molecule. Meaning if there's a reaction that can happen with that molecule, the more unstable one is the one that's going to react first. If we look at, what am I showing here? Alternatively, we can view the cyclopentane ring from above. So this is the same sort of thing that we're looking at up here, but now we're looking at it down instead of from the side. And we can see how we would represent that. And so the dashed wedges and solid wedges represent in and out of the plane. So the plane of like the screen that you're looking at. So these two dashed wedges mean they're coming out at you. Everything that's written as a line is just flat with your screen. And then anything that's dashed means it's going back into the screen, like away from you. So that's how we would represent trans and cis if we were doing these sort of skeletal structures, because we don't always draw things out like this. So be aware that rings have the cis-trans isomers. And actually, that's what we call them. Let me write that out. Cis-trans isomerism. All right, so actually to determine cis-trans isomerism in disubstituted cyclohexanes, we can view a cyclohexane ring either as a planar hexagon or viewed from above, right? So both of those representations that we looked at, because the cis-trans isomers differ in orientation of their atoms in space, we call them stereoisomers. Stereoisomers. So remember, isomers can be constitutional isomers if they're connected differently. Constitutional isomers can be stereoisomers if they have the same formula, the same connections, but different orientations, right? So constitutional isomers, these would not be constitutional isomers because constitutional isomers have different connections, right? These have the same connections. The CH3 is on the same CH3s in both compounds. Remember, that's what made constitutional isomers different for us in our examples, is that they were connected to different carbons, those groups. These are stereoisomers because they have the same connection, but their orientation in space is different, above the ring and below the ring as opposed to both below the ring. Stereoisomers. We will study more about this in chapter 15, when we look at chirality, and we'll talk about another type of isomer called enantiomers, but don't worry about it now. Physical properties. Let's talk about physical properties of alkanes now that we've done a little naming and a little of the types. So one of the most important physical properties of alkanes and cycloalkanes is their almost complete lack of polarity. They are very, very non-polar. The electronegativity difference that I was mentioning in chapter 10 between carbons and hydrogens is actually really low. Carbon is 2.5, hydrogen is 2.1, so the difference in En, electronegativity, is about 0.4. And so that puts it right in the group of nonpolar covalent. And so alkanes in general are nonpolar compounds, and the only interaction between their molecules are the very weak London dispersion forces, or instantaneous dipole forces that that I don't know if we're going to talk about in this chapter. We do at some point talk about that, I believe. If you don't remember your intermolecular forces, the weakest are those dispersion forces, and they arise from just unevenness in the location of your electrons. Sometimes your electrons are all on one side or another, giving you kind of a left side charge or a right side charge, which causes the atom next to you to have a charge, and then that all goes away very instantly. And so it's the weakest of the forces. So because it has weak forces, the boiling points of alkanes tend to be very low compared to almost any other type of compound with the same molecular weight. In general, both boiling and melting points of alkanes get bigger as you increase molecular weights. So you can see here methane being the simplest, molecular weight being 16, right? Very low. Melting point, very low. Boiling point, very low. Now, as we get more and more carbons and the weight goes up, 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 you see that the temperature actually starts to go up as well. So what this is saying is that instead of it being boiling at negative 182, now it has to be negative 1. Wait, that doesn't make sense. Why did it go down? Wait. Oh, I did the thing that I always make fun of students for doing, the negative numbers. So melting point. Okay. Which is a higher temperature, negative 182 or negative 183? Well, I think negative 182 is a higher temperature. Yeah, so that doesn't make sense. What am I looking at here? Boiling point makes sense because it's going up. Why is melting point going? Yeah, well, melting point's going up too. It's supposed to go up. So why did it go down? I don't understand this trend here. Okay, that's okay. In general, it goes up. There's going to be some situations where it goes down. Clearly, it goes down a little bit before it goes up. But in general, and if we look at boiling point, we don't have the same problem. If we look at boiling point, let's just get rid of melting point here. If we look at boiling point, it makes total sense. Methane boils at negative 164. Ethane boils at negative 88, so a hotter temperature. And that's because there's more forces to overcome. When we have lots of ethanes together, there's more chances for the carbons to overlap with other ethane molecules and to be sticky with each other. That's what intermolecular forces are. Methane doesn't have as much surface area, so there's not as much stickiness. And so as you add more carbons, two things happens. One, more of the forces, meaning more stickiness, and so higher temperatures, it needed to pull them apart. But also these chains get longer and longer, and at some point they start tangling with each other. They can wind around each other like spaghetti, and that adds to the viscosity of oil, right? To the thickness of it and the resistance to flowing and to the high boiling point. Okay. These are typically gases. These are typically liquids. Okay. Let's see. I do have an image here that kind of helps us. So the boiling points of 5 isometric alkanes. So these are all the same formula mass. They're all C6H14, but they differ in their isomers of each other. So let me draw one of these. Hexane, 2, 4, 6, 8. Wait, 1, 2, 3, 4, 5, 6. I'm terrible at this. I'm trying to do this. 2, 4, 6, where like every top is a multiple of 2. So that's hexane. What's the other one? Dimethyl butane. So 1, 2, 3, 4, 2, 2 dimethyl. So like this. So both of these are the same. Now, what's the difference in their boiling points? Hexane boils at 68, dimethyl butane at 49. So it doesn't take as much energy to boil dimethyl butane. Now, the reason for that is that it's more circular, it has a smaller surface area, and less of that interaction. Less surface area means less stickiness, right? If you have Velcro, more Velcro surface area, the harder it sticks, right? If you have a tiny little piece of Velcro, it's not going to stick to anything. Hexane has more surface area, it's longer, and therefore when you have 2 of these next to each other, there's more places for these little sticky forces to hold them together. If we have 2 of these guys together, they actually, don't have a lot of overlap spots. And so you can see that here as well as we start to change the structure. Maybe we actually drew quite a few of the isomers of, uh, of hexane. So you know there's a 5-carbon one with a methyl group on it. Or was it here? 3-methylpentane, 3-methylpentane. These are similar, and these are similar. There's actually a big gap between these two. It's neat that 2-methylpentane and 3-methylpentane, I said them out of order, have a difference in boiling point. They're very similar, but again, those little differences are going to make it harder to get close together. And in fact, in this one, it makes it easier for them to boil. This one makes it harder for them to boil. Somehow they can pack together better, like this. Somehow, I don't know. But anyways, we can see here that the shape, in addition to the number of carbons, does have an effect on the boiling point and also the melting point. They're just two different temperature ranges, but same thing melts. The same thing affects the melting as affects the boiling of a compound. So let's talk about some other physical properties as well. I probably mentioned it already that like dissolves like. This means that compounds that are similar to each other, like alkanes, are not soluble in water because they're nonpolar and water's polar, but liquid alkanes actually are soluble in each other because they're all similar to each other. They're all nonpolar like each other. Like dissolves like. Alkanes are soluble in other nonpolar organic solvents like toluene and diethyl ether, just not polar solvents like acetone and water. Density, the average density of a liquid alkane, actually listed in the previous table, is about 11.4. Where are those densities? Table 11.4, about 0.7. So you can see that here. And that's basically a higher molecular weight, higher molecular weight alkanes is around 0.8, whereas the liquid alkanes around 0.7. All liquid and solid alkanes are less dense than water, and water is 1 gram per mil. So these are all 0.7 grams per mil, right? So that's less. So they float on water. So another property of alkanes is that they are less dense than water, and they typically, the liquid ones anyways, will float on water. As far as reactions go, they are combustible, and they undergo oxidation reactions, which is a type of combustion reaction. Oxidation of hydrocarbons, including alkanes and cycloalkanes, is actually the basis for use as energy source for heat. Natural gas, liquefied petroleum gas, fuel oil, gasoline, diesel fuel, aviation fuel, all of these we can burn for energy and as not just to power electronics, but also to get heat from. They all generate a good amount of energy. You can see here the combustion of methane produces about 212 kilocalories per mole of methane. And if we were to add another couple of carbons to that, propane, you can see here that it also gets more output. So 530 kilocalories per mole of propane. So that's a lot of energy. Most of our alkanes do undergo other types of reactions as well. Reactions of halogens, for example. We call that halogenation, where methane or an alkane will react with a molecular halogen like Br2 or F2 or Cl2 and actually produce, we can think of it as replacing one of the hydrogens with a chlorine. So one of those is going to get switched out and pair up with whatever was left over. So if this was Br2, we would get CH3Br and HCl. You can see that this reaction basically happens with any kind of alkane. Here we already have a substituted alkane. Here it's CH2 with already 2 chlorines on it, and we react it, and we get a third chlorine on it, and we lost a hydrogen, so we would have made an HCl in this step, And then if we keep doing this, we can actually replace that hydrogen again with a fourth chlorine and another round of HCl. So this is halogenation, reaction with halogens, and this is a type of substitution reaction. And you can see another version of this. We've got chloromethane here. So this is like a precursor to the dichloromethane. They're a little out of order here. Methane makes chloromethane. Chloromethane can make dichloromethane. Dichloromethane can make chloroform. Basically continuing to add Cl2 to an alkane to switch out hydrogens. Now, these compounds have been used a lot, these chlorofluorocarbons. They're not great. Chlorofluorocarbons, CFCs as they're known, some of them are manufactured under the trade name Freon. You guys might be familiar with the term Freon for like your air conditioning in old cars. CFCs are non-toxic, non-flammable, odorless, and non-corrosive, right? They're great. Among the CFCs most widely used were actually CCl3F, this was Freon 11, and CCl2F2, Freon 12. These were good as heat transfer agents in refrigeration systems. They were industrial cleaning solvents to prepare surfaces for things like coatings and remove cutting oils from millings. And they were propellants for aerosol sprays. Hairsprays and such used to have a lot of fluorocarbons in them. Now, we've learned that these chlorofluorocarbons cause destruction of the Earth's ozone layer. These things act, so oxygen gas, which is what we have we have oxygen in our atmosphere, and we have ozone, which is O3. Now, oxygen gas will react with ozone, I forget in what proportion, to make no, it does something. I can't remember now what happens, but it degrades the ozone into, I believe, just more gas or something. This is not a good equation. I don't have it in front of me. What I was going to say, though, is that this equation of natural ozone degradation actually is catalyzed by the presence of these fluorocarbons, or those chlorofluorocarbons. These things in the atmosphere make this reaction happen faster, which just lowers the amount of ozone we have. So most of these chlorofluorocarbons have been replaced. The most prominent replacements are the hydrofluorocarbons, the HFCs, and the hydrochlorofluorocarbons, HCFCs. These compounds are chemically more reactive than the CFCs, but are destroyed before they reach the stratosphere. So because they're more reactive chemically, they don't make it all the way up into that high area of the atmosphere to destroy the ozone that we want to keep all harmful rays out. I think I have a. They're not complicated structures. They're literally fluorines replacing hydrogens. That's a hydrofluorocarbon, and then a hydrochlorofluorocarbon would be like. I think this is HCFC 141B, 141B. Yeah, these are the replacements. Okay, that's enough about the fluorocarbons. I think that basically does it for our alkane chapter. So again, there was a lot going on in this chapter. We named alkanes systematically. We looked at substituents for alkanes and how we talk about substituents, how we number, how we account for more than one of them. We looked at properties of alkanes in terms of their boiling points and densities, and their reactions with halogenation, reactions. We looked at constitutional isomers a little bit. We looked at conformations of alkanes and ring structures, and we looked at where alkanes come from. I think that was about it. All right, guys. So I will see you all in the next chapter on alkenes. Take care.